This is where we were. We were talking about example problems of alcohols, and I said, go try them and see what you come up with, and then come back and check your answers with me. Okay, so let's see how well you did. Let's see if you could at least draw the structures. Well, you can't draw the structures. You can't really give me the product, can you? No, you can't. So let's double check how well you remember the alcohol nomenclature rules from Chemistry 251. First one, 3-pentanol. Pent, 5 carbons. 1, 2, 3, 4, 5. 3 means third carbon in. Ding, right there. We have an all group, and that all represents alcohol. So in every single one of these, they're going to tell me, you take sodium dichromate. Well, chrome, there you go. That's all that matters. Who cares? I'm not even going to write it out. Doesn't matter. Chromium. And chromium means oxidize. Okay, so oxidation, oxidize this molecule. Erase, ding, 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 and draw an extra bond. Bing! There you go. There's your product. Yeah, it's just like that. No mechanism. I didn't tell you to draw curvy arrows. I didn't say prove it. I just said, give me the product. That's all you got to do. I don't even say to name it, because most of us don't know how to name ketones and aldehydes that these products are anyway. You simply have to do that, and you get a correct answer. What do you know? Let's take a look at the next one. 1-pentanol. But this one says with and without PCC. So that means, I got to pay attention here. And the reason that they're telling me this is because pentanol, pent is 5, 1, 2, 3, 4, and 5. And then on carbon 1, I have an alcohol group. So this is a primary alcohol. That is why they told me that. So there's 2 different options here that could happen. Let's do the first one. So 1, 2, 3, 4, 5. And here is my OH group that was there. So in the first round of oxidation, this hydrogen goes away. Bink! There it goes. The hydrogen on that carbon goes away. And we form a double bond. There you go. There's your product. But this product is with PCC, because we know that primaries can undergo another oxidation step. So 1, 2, 3, 4, 5, and we have a double bond right now on that carbon and a hydrogen out here, right? But another round of oxidation could squeeze an oxygen in there. And there's our carboxylic acid form. So this would be the traditional chromate, sodium dichromate, with the acid. And up here at the top would be the addition of the PCC that we've talked about that stops it after that first oxidation takes place. So there's your 2 answers for your second example for 1-pentanol. All right, let's look at another. 2-methyl, 2-pentanol. All right, pentanol, pent, 5. 1, 2, 3, 4, 5. 2, right there. We have an all group, that's an OH. And on 2, right here, we have a methyl group, so another carbon. So it says what's going to be formed when this is reacted with sodium dichromate and acid. Okay, well, oxidation is going to happen. And oxidation is going to come in, and it's going to say, bink, away that hydrogen goes. And then it says, oh, I'm supposed to erase another hydrogen, though, aren't I? Folks, look at this. This is a tertiary alcohol. Shame on you. This is a tertiary alcohol, and that tertiary alcohol, no reaction is going to go forward. Tertiaries do not undergo oxidation reactions. Tertiary alcohols, at least. So no reaction's going to happen here. Nothing. Let's go to the next one. That was an easy one, by the way. 2,4-hexane diol. Ooh, they're getting fancier. I like it. So hexane, hex is 6. 1, 2, 3, 4, 5, and 6. 2 and 4. So carbon 2 and carbon 4. There we go. 1, 2, 3, 4. And on each one of these, I have diol. So di means 2 in total. Where are those 2 OH groups? Those 2 OH groups are located at number 2 and number 4. There we go. This is a secondary. That's a secondary. So both of these can undergo oxidation. So what happens here with this reaction? Bink goes away. Bink goes away. They both react, and vyomp, vyomp, 2 double bonds get formed. And it's okay to do this. I mean, that's what's going to happen. Nobody said that you can't do it with 2. One is just like the other. So what the neighbors are? So on the second carbon, we have a double bond that gets formed. That's a ketone. And then on that fourth carbon, we have a double bond that gets formed. And folks, that's a ketone as well. So in each one of these cases, I have a ketone on those carbons. I have 2 ketones. Perfectly fine. No big deal. There's the product for 2,4-hexane diol. Next one, cyclohexanol. Okay, cyclohex, 6 carbons. Okay, that's fine. There we go. There's my ring. And it doesn't really give me a number. Where do I put the all group? Oh, wait, it doesn't matter. It's a ring structure. So wherever you put it, you're going to start there with number 1. And they just don't even bother writing down number 1. So I'm just going to write it here. There we go. Put it anywhere. That's the magic of organic. So now we have to oxidize. Oxidation reaction goes on. This oxidation reaction is going to use chromium, chrome. And you're going to dink that hydrogen off. And an extra double bond is going to form. An extra bond is going to form to make a double bond. Well, that's still a ketone. No big deal. The reason that happened, it was a secondary alcohol. That OH was attached to a carbon. That carbon's attached to 2 others. And a hydrogen. That's its 4th bond. So that hydrogen and the one from the OH group was removed. And a double bond was formed in between them. Finally, the last one was 1,4-butane diol. Okay, so butane, but is 4. 1, 2, 3, and 4. 1 and 4. So on 1 carbon and 4 carbon, I have diol, which means 2 alcohol groups. Where are those 2 alcohol groups? On spot 1 and spot 4. And an oxidation reaction is going to happen. Chrome is going to be added. Same thing like before. Ding! Ding! There we go. And a double bond gets formed here, and a double bond gets formed there. Now, keep in mind, this 4th bond is to a hydrogen, and this 4th bond is also to a hydrogen. So in the initial stages, hint, 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 in the initial stages, these form aldehydes on both ends. However, the first carbon was a primary alcohol. The 4th carbon was also a primary alcohol. That OH group was on a carbon that was only attached to one other. So just because there's 2 groups doesn't mean the rules change. We saw this before. So this would be the first stages, and this would stop if PCC was added. But it really didn't say that in the example problems. It just said 1,4-butane diol for this one. Now, the 1-pentanol, it told me that, with and without PCC, but it didn't tell me that here. So I have to assume that no PCC is added, which means oxidation is going to happen again for a second round because these are primary alcohols on both carbons. So what happens now is the oxygen will squeeze in here and it will squeeze in there. And now we have formed a carboxylic acid on both sides of that molecule. So folks, this is a summary of the chromium-based oxidation reactions for alcohols. Hopefully you'll find that these are not very difficult. The mechanism might be, right? But that's just like a little cherry on top. Really the point here is predicting the products, kind of understanding the mechanisms of the reaction as far as what kind of structure gets ended up with, not necessarily curvy arrows every single time. Again, they're great to know, and you should understand why they happen. And you should be able to flow a mechanism from beginning to end and follow it. But really, the most important thing here is here's your reagent, here's your starting piece, your organic, what kind of product gets formed. Now, as you know, other videos, so far, you've seen alternative versions. And we do have an alternative version for oxidation. And here's why. Chrome! That's a problem. When we use chromium in a laboratory, we can't just dump it down the drain. The issue here is that chromium is an environmental hazard. It could be a health hazard. So whenever we work with chromium compounds, we really do take an extra step to gather those materials that have touched chromium, or paper towels that have chromium waste, reagents that are not used with chromium, any of our products that still have chromium solvent left in them, and the chromic acid that we are using in these oxidation reactions. All of those cannot go down the drain. That is a hazard. And some of us just don't want to worry with that crap. Why do I want to worry with it? Why? Okay? So if there's another alternative form out there that I could use to do the same job, then this other option might be a little better for me. Maybe for my lab, the place that I'm working, what I'm doing. That will save me a lot of disposal fees. That will save me a little bit of hazard fees. That will save me the headache of keeping up with the waste if I can pick something that's maybe a little bit more environmental friendly. And the option here is using something called sodium hypochlorite, NaOCl. Now, NaOCl is not the only thing that gets added onto these arrows. They very often will write CH3COOH down here at the very bottom. And they keep this at 0 degrees C. Now, once again, your refrigerator is 4 degrees C. So this is not freezing, all right? But 0 degrees C is pretty cold. So what they're telling you here is take sodium hypochlorite and acetic acid and put it basically into an ice bath and allow something to react. That's not unheard of. It's very easy to do. And if you're in the chemical technology program at Cape Fear Community College, you actually do this reaction. This NaOCl, this goes by another name. Sodium hypochlorite goes by the word bleach. That's right. That's all you need. If you can put bleach in your washer at home and dispose of it, we can do the same thing in the lab. Look at how much easier that made my process to be. And then the acetic acid that's down here at the bottom, yeah, this acetic acid is typically glacial acetic acid, which means super, super strong. But folks, it gets weakened down. It gets water diluted down with all of the other reagents that need to go in it. And then at the very end of this, I typically neutralize this step anyway. And as long as we neutralize that acid, we can pour it down the drain as well. So this is a more environmentally friendly way to oxidize an alcohol. I take bleach, sodium hypochlorite, mix it with some acetic acid, put it into a container. That container probably has a nice little ice water just to keep it cold. And the reactions happen the same way. There's no difference. So once again, if you have a secondary alcohol, you will make a ketone. If you have a primary, that will go to an aldehyde. There's no difference in what we've just learned with the chromium as there is with the bleach. There's no difference at all. If you want to know the mechanism, this is what it looks like. I'm not going to go through it fully and draw it out step by step. It pretty much is the same thing. So here's the sodium chloride here, the bleach. Here's an alcohol. It just happens to be on a ring. That OH group is attracted to that hydrogen, says, hey, come here. And that hydrogen goes, okay, bye-bye. And away it goes. And these electrons get shifted to the oxygen of the O and the Cl. The O and the Cl now become negative. That turns into a nucleophile. And that nucleophile comes in, and it knows that this OH group is now in trouble. The reason is because that has now been protonated, and that protonated alcohol group turns into a good leaving group that we call water. So the OCl goes in, and it substitutes for that leaving group. And that's what you see up here on the top right-hand side of that ring. Now, we're not going to leave that area alone. There is another hydrogen that's here as well. This oxygen's electronegative, that chlorine's electronegative. They're all fighting for electrons. Water comes into the picture that was just released and says, I'm not done with you either. That water goes in with those free pairs of electrons, pulls the hydrogen off, bink, away it goes. A electron shift happens to form a double bond between that carbon and that oxygen. Hence, this is how we generate the ketone functional group. And then that chlorine says, fine, I've had it with you. It takes the electrons and it leaves as the chloride ion. So we still have a little bit of acidic conditions. We have some negative ions that are floating around. And we end up with ketones or aldehydes at the very end of this process. There's another alternative way in order for the oxidation to happen as well, and this is called the Swern oxidation. So Swern oxidation, folks, the word oxidation's in the name. That means you take an alcohol and you bink a hydrogen and bink a hydrogen and you draw a double bond in between them. And that is what happens over here. The same thing happens with the secondaries. You bink the oxygen, bink the carbon, and draw an extra bond between those two, and you get the same type of products. There's no difference in the product formation. That's a very good thing for us. We don't have to learn anything new. But it's just a different set of reagents that do the same thing. This one's even more stupid. All right, and the reason is because this goes to -60. I've got to be able to perform this reaction at -60 degrees. Okay, well, I don't know about you, but I am not thrilled with the idea of performing a reaction at -60 degrees in order for this to go forward. So this is just fluff. That's all that this is. It's a fluffy little reaction that they say, ooh, look at what else we can do. We can bring in this reagent and we can put this to -60. I mean, that's really all that this is. Because out of the three choices so far, it looks like bleach and vinegar is going to be a little bit more environmental friendly, and it's also going to look a little bit easier to work with. It's not as hazardous as the chromium is, and 0 degrees, not very hard in order to do that reaction with. Here, though, -60, that's a different story. So this set of reagents can be used in order for oxidation to happen. What is required here is something called dimethyl sulfoxide. So that's this molecule. There's a methyl group, there's a methyl group, and the S double bond O is the sulfoxide group. So there's dimethyl sulfoxide. The next one is something called oxalyl chloride. All right, so oxalyl chloride. Here's the chlorine on a carbon, on a carbon, on a chlorine. So there's that. And this has two ketones, not really ketones, but two carbonyls that are on that group, that molecule. So C double bond O, Cl, C double bond O, Cl. That's oxalyl chloride. And then finally, triethylamine. That is written in step number 2. So the first step happens first. Then they throw in triethylamine maybe a little bit later, and that just helps the oxidation to go forward. The triethylamine, they do not give you a structure for. If you go back and remember Chemistry 251, the amine group is a nitrogen-containing group, and triethyl. So 1 carbon, 2 carbon, 1 carbon, 2 carbon, 1 carbon, 2 carbon. So this is actually a CH2, and this is a CH3 all the way around, and a free set of electrons for the nitrogen. Remember, nitrogen only wants 3 bonds. That's where its formal charge is 0. So once again, same products. You'll get the same ones whether you use this. You'll get the same ones whether you use the bleach, and you'll get the same ones if you use the chromiums. Either one, perfectly okay. Again, variety is the spice of life, but variety can also make you hate organic chemistry. Now, before I finish up the oxidation step, I alluded to the fact of ethanol. So with ethanol, we're getting to a point that we can start putting pieces together. And you probably have heard of blood alcohol content. If you were drinking and you were pulled over on the side of the road by a cop and he tells you to get out of the car and walk a straight line and you fell it, they can bring out the good old breathalyzer. There's a couple of different versions of breathalyzers. One of the early versions of breathalyzers was this contraption that used oxidation reactions in order to help determine how much alcohol was in your system. All right, so here's the nutshell of the blood alcohol content test. When you drink, your body absorbs the alcohol, right? You're processing the alcohol, and you get an equilibrium. An equilibrium is basically equal on both sides. That's Chemistry 152. You probably had months of equilibrium lecture stuff in that class. KSP, KAs, KBs, ice charts. You remember all that stuff? That was all equilibrium. So equilibrium is going to come in, and it will be equal amounts in your lungs, arteries, and in your blood, and in your breath. They're all going to be equal. And the blood alcohol content is, of course, based on your breath. That's why you blow into an instrument. So when you blow, you would have little molecules of ethanol that's coming out of your breath. Some people don't need a breathalyzer. You can smell it on them. Again, you can smell the alcohol. You've been there. You probably know somebody that does it. But this is a scientific way to measure that. So this alcohol basically goes through a chamber. Whee! And that alcohol molecule can be oxidized. We know that now. We know what to oxidize it with. And this, in the very beginnings of the early breathalyzer test, was a chromium-based tube. There was something in that tube that was chromium-containing. Why? We know it will oxidize. And the good thing about chromium is that when it oxidizes, folks, it turns color. The dichromate, which is the beginning reagent, is a very orangey color, maybe brown in some instances. So when we make this potassium dichromate or sodium dichromate and we put it in sulfuric acid, this is an orangey brown liquid that gets toted around. And if we pump alcohol into that system, oxidation takes place. You know how to predict those products now. You know what's going to form. And as that oxidation is happening, the chromium changes the charge. It's a transition metal. It's a valley metal. That's the whole thing with transitions. They can flip-flop back and forth between charges, +1, +2s, +2s, +3s, +2s, +4s. It's transitional. That's what that means. The valley. Chromium is one of those metals. Because of that, chromium starts off orange. As the alcohol gets pumped in, it reacts with the chromium. The chromium changes the charge because of the oxidation reaction. Oxidation, right? I told you it had something to do with electrons. And because it changes the charge, it goes from orange to green. And the instrument that they hold in their hand measures the green color. That's how some of the older blood alcohol breathalyzers worked. That green color was measured. That green color was measured using a UV vis spectrometer that was built inside of the instrument, a very portable device nowadays. But this began to get modified and it began to change, and we improved the breathalyzer over the course of time, and it doesn't necessarily work like this anymore, but this was an early version of the blood alcohol content test. It was a chromium-based test that used UV vis spectroscopy to pick up colors, and chromium that had not been used was an orangey color, and chromium that had been used in order to oxidize the alcohol, that changed color to a green. The darker the green, the more alcohol was present on the person's breath. There you go. There's your life lesson for the day. So the issue here is, can I put a penny in my mouth and beat the breathalyzer? And the answer is no, you can't. It doesn't work, folks. I mean, if you want to take the gamble, go ahead and try it, but it does not work because that's not how the test works. It doesn't work that way anymore, especially now in the modern breathalyzers. So you can't beat the blood alcohol content test. What will happen, though, is if you put a Listerine patch on your mouth, that's going to peg alcohol. If you actually just put in some Listerine and swish your mouth in with it and spit it out, that's also going to be pegging high in alcohol. Oh, now you see the problem. If I put wine or beer or alcohol in my mouth and swish it and spit it out and not even drink it, that's going to be in my mouth, and I'm going to blow into that machine, and that will peg high. That's something else I don't want to happen, right? If I want to keep my license, which is another reason they get you to do the field test first. They let time go by just in case you do have something in your mouth that could peg positive. They know really how long you should give someone to make sure nothing is in their mouth, make sure it's completely cleared out. Maybe you did put Listerine in your mouth because the cop was hot. That pulled you over. You want to put on the best face possible. Well, if that was the case, and you put Listerine in, you would fail the breathalyzer. But they give you time to wear that off before they go any further with the test. One of the reasons that they do it. All right, so there's a review or a rehash of this BAC known as blood alcohol content. All right, so that's where I'm going to stop this video. In the next video, I want you to do some more example problems on your own. And here's a list. And it says, what product is obtained from the reaction of the following alcohols with H2CrO4, HOCl, and the reagents required for a Swern oxidation? So I want you to answer 1 through 6. Those are your alcohols right there. We kind of already done it, though, with part A, haven't we? Those were the same alcohols we did before. and we reacted it with chromic acid. Now they want you to go back and do with the OHCl, the bleach, and they want you to go back and do it with the reagents for the Swern. So see what you can come up with, and then get back to me. Let me know what you find out, and hit play on the next video.